place where it's warm. So thank you all for having me here at College Station. I apologize if my voice gets a little bit scratchy. I'm just getting over a cold, but I have my bottle of water here. I want to point out, as soon as I make this go away, that this talk is based on a few papers, one of which is literally showing up a couple days once the archive sends out its next mailing. So this over here was just submitted about an hour and 5 minutes ago, and I'll be able to show you a couple of plots from that paper that you'll see on Sunday night. So, as the title suggests, I'm talking today about direct detection. I want to start with some context for direct detection in the history of dark matter physics. And there's no more important context for this than WIMPs. Right, so for the last 4 decades or so, we have been guided both theoretically and experimentally by this idea of weakly interacting massive particles as a dark matter candidate. And there has been a very successful experimental program to probe the WIMP parameter space. I want to show you a recent summary of some of the outcomes of these searches. This is a review from some time ago. I want to read the last line of this abstract to you. It says, "The moment of truth has come for WIMPs. Either we will discover them in the next 5 to 10 years, or we will witness their inevitable decline." This was about 10 years ago this review was published. Still no WIMPs. And now we are used to seeing titles a little bit more like this. So given that we have not discovered any WIMPs, we now have 2 choices. We can take a model-driven approach where we do essentially what has been done for the WIMP over the last 30 or 40 years, where we find new lampposts, new promising models that solve multiple problems, invest heavily in those. Or we can take a more systematic approach, which is more model independent, where we start from the presumption that maybe nature is more clever or uglier than we thought, and we design probes that are sensitive to a very wide array of models. I'm going to lean a little more towards the model independent side of this talk. I want to stress that we absolutely need both of these approaches right now. And to justify that statement, let's take a look at what we're up against. This is the dark matter parameter space, or as one slice through it. This is just the space of masses that one can have for a dark matter particle. It is 90 orders of magnitude across. We've spent most of the last 4 decades probing a subset of that red band. Now, there are a couple other islands here that have attracted a lot of interest. Axions at lower masses, fuzzy dark matter at really light masses, compact objects like primordial black holes at very high masses. I'm going to focus for this talk on light dark matter. But when I say light dark matter, I really mean from the keV scale for fermions or down to the millieV scale for bosons, up to roughly a GeV. And I'll justify those scales for you shortly. I do want to point out, if you really want to look for opportunities for direct detection that are far from the weak scale, you don't only have to go low. In fact, there are a couple of things I've done over the years that are actually geared towards detecting compact objects in a sort of direct detection fashion. And this paper was just out a few months ago. It's really, really fun if you like direct detection ideas for black holes. So you can go check that out, or you can ask me about it later. But let's come back to this light dark matter window. So here's what I want to do with the rest of the hour. I'm actually going to start by talking about how we can take advantage of condensed matter physics to probe dark matter in this regime. I'll explain why we have to do that and sort of what we actually have to do to get down to this scale that I told you about, the keV scale. Then I want to take some time to talk about anisotropic systems, and in particular, how we can take advantage of this condensed matter physics I'll tell you about to achieve directional sensitivity. And I'll explain in a moment why that's such an important thing to do. And then towards the end, what I want to do is actually give you some real examples of these ideas in action. And in particular, I want to show you some results from actual prototype experiments using superconducting detectors that set real constraints on dark matter physics using some of these ideas. All right, so let's get started. And I want to start with just the context for light dark matter detection. Why is it challenging to probe light dark matter? Well, if you look at the results from a direct detection experiment, you always see a plot like this, right? Where you have the dark matter mass on the horizontal axis, cross-section on the vertical axis, and you'll always see these constraint curves die off at low masses. That's kinematics. This is just the point at which the mass of the dark matter becomes lower than the mass of the target with which it is scattered. In a typical plot, for example, from xenon, that target is a nucleus. So the mass scale is GeV. And you can see that indeed this curve starts to jump up around 10 GeV, around the mass of the nucleus. Now we'd like to go down about 6 orders of magnitude. Is there a question first?
Sorry to interrupt.
Yeah.
I thought that the constraint down there is that the kinetic energy of your dark matter particle is not much less than the target, but much less than the threshold of your detector.
So that is also true, and you need a low threshold detector in order to go further down. But this sort of power law-ish rise here is just that the kinematical matching is bad. Like if you write down what's the maximum energy transfer you can have, it doesn't matter how much energy you have available. You literally just can't kinematically transfer the energy.
Sure.
So we want to go down 6 orders of magnitude. Why 6? Well, it's not just because of the models that live in space. It is pretty easy to write down, for example, a freeze-in model where you can make the dark matter at these lower masses. But really it's because there are good guideposts as we go down further. So at the KeV scale in particular, we have stringent constraints from cosmology that tell us that if dark matter is fermionic, it has to live above the KeV scale. If dark matter was bosonic, of course, it could be lighter. But in that case, actually, it turns out that going to the KeV scale is still the right thing to do, because if you want to look for a light boson, an ultralight boson, then you're not going to use a scattering type experiment, right? Well, ultimately what you want to do as you go to very low masses is have some kind of resonant cavity. So where does that become effective? Well, really, you would use that approach below about 1 millieV. And if you can build a scattering experiment, which is sensitive to fermion scattering at a KeV, then you also are sensitive to absorption at the millieV scale. So if we can target the scattering of fermions down to the KeV scale, we will probe this parameter space of light-dark matter interacting with our detectors. Okay? Now, one of the easiest ways to go down further in mass from the GeV scale that I highlighted before is just to use a lighter target, and we can use electrons as a lighter target. So this was sort of the silly idea that people started doing now almost 15 years ago, where because the electron is just lighter than a nucleon, the dark matter mass is better matched to the target mass, the kinematical issue goes away, and you can make constraints like this. These are actually real constraints from experiments that constrain dark matter down to about the MeV scale, the electron mass. And these are actually limited largely by threshold. So there are lots of proposals to actually build experiments that have lower thresholds than these and be able to go further down in mass from the MeV scale to accomplish those last 3 orders of magnitude. Now, there are going to be issues with that, as I'll explain in a moment. First, though, I want to come back to this issue I raised before of directional sensitivity. I said before, we really want to have some kind of directional sensitivity in a dark matter experiment. Why is that? Well, it's because we expect the dark matter in the lab to have a direction, preferred direction. We sit at some point in our galactic halo. We are going around the galactic center. That means that there is a dark matter wind in the laboratory frame. As the Earth rotates during the course of the day, the direction of that wind changes. So if you have an experiment that has anisotropic sensitivity, you will see a daily modulation in the dark matter scattering rate. Now, that daily modulation is extremely important for actually implementing these low mass scale searches. And the reason is just backgrounds. Ultimately, even at higher masses, experiments have been limited by backgrounds for a long time. There is a very famous case of the Dama experiment, which has recorded a signal that has been in tension with other observations. If there was some kind of directional signature in that experiment, we'd be able to know for sure what we're seeing. It wasn't designed with that capability. So we really want experiments to be able to go down to the KeV scale with directional sensitivity. If we can do that, not only will we be able to actually confirm a dark matter discovery, we'll also be able to actually cut through parameter space much more quickly. And the reason is just that you can toss out any background component that's isotropic. So you look in your experiment for an anisotropic signal on top of the noise. All right, that's what we want out of a dark matter experiment. What is so hard about getting there for those next 3 orders of magnitude? It's the condensed matter physics. The problem is that if your dark matter is lighter than a GeV, but really lighter than an MeV, now the dark matter cannot be thought of as just scattering with a single electron in our case. And that's just because the actual scale of the momentum transfer and the energy deposit is not larger than the scale of the potentials that those particles feel in the material. So because of that, we have a few issues. The actual scattering rate becomes incredibly difficult to compute. There are suddenly these collective excitations that contribute to the dark matter scattering rate. If you try to do the whole calculation from the ground up, you then bake in your dark matter model dependence into that whole calculation. This has led to enormous confusion in the literature, where some dark matter model dependence has ended up seeping into these calculations of scattering in materials. So I want to encourage a very simple viewpoint for the rest of this talk. Let's not think about billiard ball scattering, okay? Really, our detector is just some system with some set of eigenstates. The dark matter is just going to cause a transition between 2 of those eigenstates. What those eigenstates are depends on the condensed matter physics. This is in one sense a challenge, in the sense that you have to understand what those eigenstates are. It is also a tremendous opportunity, in the sense that if you can control what those material eigenstates are, now you can engineer a system that has favorable states for dark matter scattering. Now, what I want to do for the next 15 minutes or so is talk you through one setup where you can actually understand how the different material properties affect the dark matter scattering rate. You can do controlled calculations where you can understand how to build a good experiment. So let's talk about that in the context of dielectric materials. These are just materials that have a dielectric response. The electrons move around a little bit in response to some deposited energy and momentum. The key idea of what I'm about to show you is just that you can separate the probe, that is the dark matter scattering potential, from the response of the condensed matter system. So you are going to think about the scattering process as follows. We have dark matter that comes in. It has some single particle interaction potential, the ordinary potential you would write down for scattering with 1 electron. And then there's some response function that describes the response of the material, which is totally factorized away from that potential. If you go and ask your condensed matter friends what this epsilon is, they will tell you it's nothing but the complex dielectric function. It is literally the same dielectric function or dielectric constant that you learn about in your first year of E&M. It's just the ratio of the applied potential to the total potential of the system. Quick aside on notation, I'm always going to use Q for the free momentum transfer. I'm always going to use omega for the deposited energy in the scattering process. So if you have a non-static process, this epsilon acquires a space-time dependence, which under a Fourier transform becomes this momentum and energy dependence. This energy and momentum dependent dielectric function turns out to characterize everything about the condensed matter system's response to dark matter scattering. And I want to emphasize, again, this is the same dielectric function that you know from E&M. So the same quantity that tells you, for example, about how a material will screen if you apply an electric field will turn out to have consequences for dark matter scattering. And I will, in fact, show you an analog of that same screening for dark matter scattering. Okay, let me show you how this actually works in practice. What we can do is write the dark matter scattering rate in the following form, where here I have factorized away the potential with which the dark matter is interacting from this piece in blue that is called the loss function in the condensed matter literature. So this loss function describes all of the condensed matter physics in the problem. It is the imaginary part of -1 over epsilon. I'm going to say a few more words about where this comes from, but first I want to tell you why this is so useful to be able to write. First of all, this formalism, you write things this way, the scattering rate becomes eminently predictable. The huge uncertainties that come from having to deal with understanding the eigenstates of the system are reduced to just understanding this dielectric response function, epsilon. So as long as you can borrow some technology from the condensed matter literature, where they've studied this epsilon for a long time, you can readily write down approximate forms of this loss function. You can also use this in an empirical way, in a data-driven way, because this epsilon is the same epsilon that controls standard model interactions with this condensed matter system. So that means that you can use electron scattering or X-ray scattering. And you can actually measure epsilon in a particular system. You can calibrate your experiment. Then you can go back and put that into this scattering rate and extract the dark matter scattering. This is also extremely flexible. If you want to use an electron scattering style experiment, then basically any system that isn't terribly exotic can be described in this language. And since you only care about the dark matter and the non-relativistic limit, this is basically the only potential you ever have to write down. This is what you get if you have, for example, a scalar or a vector exchange, right? In the non-relativistic limit, it looks the same. So for any spin-independent interaction in particular, this is basically universal. If you have a spin-dependent interaction, that is a very different story. I'm happy to say a few words about what that would entail. But for the purposes of what I'm going to show you, everything here is spin-independent. Okay? Okay. Last thing I want to mention about this formalism is that this computation is, in a sense, all-inclusive. If you trust your calculation or your measurement of epsilon, then you have characterized the contribution of all possible collective modes in the material to the dark matter scattering rate. That is actually very important, as I'll explain in a few slides. Okay. I want to say a few more words about where this imaginary part of -1/epsilon comes from. This is actually a little bit of a historical accident that the scattering rate got written that way. Really, the materials physics enters the problem through Fermi's golden rule. You write down this dynamic structure factor S. This is what actually controls the dark matter scattering rate. You can see here, it's basically a sum of all the matrix elements of the electron density operator between the initial state of the material and possible final states. So this is where all those different material eigenstates can enter. This object, in principle, you can compute directly, and this is something people actually used to do, actually computing basically wave function overlaps, but that's actually a much harder way to solve this problem. What you can do instead is take advantage of the fluctuation dissipation theorem, which tells you that since S is really the spectrum of the electron number density operator, it has to be related to a linear response function like this. And that linear response function turns out to just be related very simply to 1/epsilon. So the fact that we have this like funny imaginary part of -1/epsilon, that is simply an accident of the way that we first wrote down the dark matter scattering rate. Really, the object that matters for dark matter scattering is the linear response function that corresponds to the dynamic structure factor, which happens to be pretty simply related to the inverse of the dielectric function. Okay. Now what I want to do is actually show you what we can do with this response function. So this response function you can write down as a very simple correlator, which you can evaluate with your favorite diagrammatic techniques. You can literally write down all the loop diagrams that contribute to this correlator. Let's make an approximation so that we can actually do something controlled. We are going to say, usually, what you would do to calculate this response function is you take all the 1-pi diagrams, or all the one particle irreducible diagrams, and you would sum them up in this big geometric sum. What we can do to get an approximation is to just drop all the one particle irreducible diagrams except the single bubble. So we can say that there is an approximate form of this response function, which is just that geometric sum of the single bubble diagram. This is actually, it corresponds to something that's called the random phase approximation in the condensed matter literature. It's been extremely well studied, and it actually has a couple of really key features that we want to understand for the purposes of dark matter scattering experiments. So let's work with this random phase approximation, or RPA dielectric function, for a little bit and see what happens. I want to show you that you can actually write this down explicitly. You can really do this computation. This is what it looks like. It's called the Lindhard dielectric function. It is ugly. The only reason that I'm showing it to you is to prove to you that you can indeed write this down in closed form. And there's a couple of features that I want to highlight here. There are a couple of material parameters that show up as undetermined parameters of this dielectric function. One of them is this omega p over here. That's the plasma frequency. It will turn out to be the energy of resonance in the system. And then there is this width gamma that shows up. That's the width of that resonance. Now, let's see about those collective effects I keep on talking about. One thing I promised you earlier on is that there was going to be an analog of screening in dark matter scattering. This is really exactly the same as screening in E&M, where if you apply some field, the charges in the system rearrange themselves to partially cancel out that charge and reduce the potential in the system. So this is what happens for dark matter scattering, exactly the same physics. If you do a naive calculation of a dark matter scattering rate, just by computing the rate over scattering of individual electrons, you get this purple curve over here. So you can see that you get very, very, very small cross sections for very small dark matter masses. However, if you use this random phase approximation, if you use this dielectric function formalism, you get the orange curve. That's 12 orders of magnitude or so at the masses that we care about. So this is a little bit depressing, but I want to point out a couple of things that are really important to bear in mind. First of all, this screening effect is a property of the material response. I did not have to make any statement about the dark matter model apart from the spin independence to say that this screening should happen. And in fact, there was a long argument in the literature for several years about whether or not scalars and vectors would be subject to screening in different ways, because the physics appears to be very different. If you try to just go from a diagrammatic language to understanding why various interactions should be screened, well, a vector, you can say, okay, my vector is going to mix with the photon. And so now I can understand that in the same way that the photon field is screened, I'm going to screen my new vector. But then the scalar doesn't do that. So why does the scalar get screened? And then there was a long argument about are there other modes in the material the scalar can mix with. It turns out that's, in a sense, a red herring. You just have this material response that is independent of the dark matter physics, and that gives you the same screening effect. Now that was depressing. That eroded the sensitivity of an experiment. Let me show you something a little happier. There's another collective excitation in a typical dielectric system, and that's actually contained in this random phase approximation. That's a plasma. So what's a plasmon? If you Google it, as I did some years ago, you will find out that it is a brand of biscuits for babies, apparently. I guess this is one more step in a proud tradition of us naming our particles after things we find on the shelf. But really, what is a plasmon? A plasmon is a collective mode in the electron system. So really what this is at a cartoon level, the electrons are sloshing back and forth. So that actually corresponds to a peak in the loss function. If you actually go and measure the loss function of a typical material, you will see this big resonance at this plasma frequency. Now, you should object to me showing you this plot and claiming that it has anything to do with this light dark matter scattering. Why is that? Because look at the energies here. This peak, this plasmon peak, is centered at around 15 eV. If I want to probe dark matter scattering below, say, an MeV, I really need to be sensitive to energies only below an eV. So why does this have anything to do with dark matter scattering? Well, even if you have a plasmon that is located at a fairly high energy, that doesn't mean that it's unimportant for the lower energy scattering. So if you kind of use the same RPA, random phase approximation, dielectric function, and just continue down to lower energies, you can actually be in a situation where at substantially lower energies, well off peak from the plasmon, you still actually get a substantial contribution to this loss function from the plasmon. I want to reiterate, just to keep you oriented, that this whole function that I'm showing you, this loss function here, the scattering rate is directly proportional to this object. Where this object is big, the scattering rate is big. So here, if you have this enhancement of the green curve from having a wide plasmon, that actually can be several orders of magnitude in the dark matter scattering rate. Please.
What are the limits in which you can actually do the partitioning? So you wrote down gamma as like this P of Q square and epsilon, but you didn't tell like what the Q can be. But are there any limits on like what the Q should be or?
The momentum transfer.
Yeah.
Oh, absolutely. So here, so I plotted this at 10 eV, right? That, for all intents and purposes, is like zero momentum transfer. Typically, the momentum transfer in a scattering process will be much higher if you're looking at, say, MeV scale dark matter. The reason that I plotted it down here at like 10-ish is just that the limit to Q equals 0 is sort of a simpler story. As you go to higher momentum transfer, the plasmon itself, the plasmon dispersion sort of changes very sharply. So above like a keV or a few keV of momentum transfer, it will not look like this. And that actually will be very important later on.
And when did the epsilon story break down? Like at what Q can't leave you?
Well, the whole story breakdown.
Yeah.
Much higher. Yeah, for basically everything that I mean, so you do have to assume that you have a small perturbation, right? So it can't be arbitrarily large, but many keV, and you're still safe. All right. Good. So let's just summarize a few things that we can learn right away from this random phase approximation that gives us this Lindhard dielectric function. First of all, we have this generic screening effect at low masses. Second, we have these additional resonances, these plasmons that can enhance the dark matter scattering rate. And third, that the width of these plasmons can be a controlling factor as well in the dark matter scattering rate. So now that we have this analytical form of epsilon that we were able to use for some heuristics, let's actually see how we can build a better experiment with these ideas in mind. So I want to show you, this is what the dielectric function, what the loss function matter looks like as a function of energy transfer and momentum transfer together. This is a very ugly picture. I'm going to reduce it to cartoon form for you. So here, this is the momentum transfer on the horizontal axis, the deposited energy on the vertical axis. And the first thing I want you to pay attention to are just these three shaded wedges. Those are the wedges that are kinematically accessible to dark matter scattering for a fixed dark matter mass. So if your dark matter has a mass, for example, of 10 MeV, it can hit everywhere within this wedge. That's just because of the dark matter's speed in the lab. Now, if you neglect the plasmons, if you neglect these resonances, this is a rough contour of what the rest of the loss function looks like, this gray band over here. And then this blue piece here is the contribution from a plasmon. So before I showed you that nice peak, right? That peak was a vertical slice through this plane. But really that plasmon peak extends some way in momentum transfer above a few keV for a typical material. That plasmon disappears. Okay. Now you might look at this and say, actually, this is kind of unfortunate because it looks like the plasmon just sort of barely leaks into the dark matter's accessible region. Right. So wouldn't it be nice if we could actually get the dark matter to excite one of these plasmons directly? Well, let's think about what would actually need to happen in order for us to do that. At full momentum transfer, if we want the plasmon to be accessible to dark matter scattering, you can do a little bit of algebra to convince yourself that that corresponds to the condition that the Fermi velocity of the material should be lower than the dark matter velocity. It's a very nice rule of thumb. it turns out to actually be even more useful than just the plasmon. If you were to ask, in the absence of a plasma, what would it take for the dark matter to be able to excite the, or to hit the largest value of the loss function in the absence of a plasmon? It turns out to be exactly the same condition. What you want for a large dark matter scattering rate is a target with a small Fermi velocity. This is slightly unfortunate because Fermi velocities are typically a little bit larger than the dark matter velocity in our galaxy. So we have to get a little bit clever to think what kinds of targets are going to have low enough Fermi velocities to get an appreciable enhancement from these condensed matter effects. Now, there are a couple of possibilities. Dirac materials, for example, have Fermi velocities that are fixed by collective effects. So they're not the sort of typical order 10 to the minus 2 velocities that you find in most materials. And then there are heavy fermion materials, where here the electron has an effective mass in the material, which is not the bare electron mass, that actually changes the Fermi velocity relative to the Fermi momentum. And so that actually also gives you this low Fermi velocity, which can enhance your scattering. So with that in mind, with those heavy fermion materials in mind, now I can tell you what that orange branch is. That is the plasmon in a heavy fermion material. That's uranium, ruthenium, silicide. It's the first thing you find if you type into Google heavy fermion material, which is what we did. And you can see that this plasmon actually becomes kinematically accessible to the dark matter. Now, given that, if I were to just make a plot of the reach in a dark matter experiment made of different materials, I should expect that this uranium, ruthenium, silicide material should do whatever another material would do at higher dark matter masses. But when the dark matter mass is around 100 keV, there should be a large fractional contribution to the scattering rate from this plasma. And so I should see the sensitivity improve pretty dramatically right around that mass. Let's see. So this green curve over here, that's the uranium, ruthenium, silicide. If you were to look only at a dark matter mass of a GeV over here, you would say this material is useless. It's outperformed by, for example, aluminum by many orders of magnitude. But now go down to 10 to 100 keV, and you see that because you have the plasmon dominating the scattering rate, you have a dramatic enhancement of the dark matter scattering rate, dramatic enhancement of the sensitivity, and you actually beat aluminum, for example. So this particular material, this uranium, ruthenium, silicide, it's not something that you'd want to build a dark matter experiment on. Any thoughts why? I don't want to build a sensitive experiment out of radioactive materials. Thank you. So indeed, you probably don't want to use uranium, ruthenium, silicide to build a dark matter detector. But what is so nice about this is that it took us literally a few minutes to make this green curve once we figured out that we should be looking at uranium, ruthenium, silicide. And there happen to be databases of the dielectric function for many, many different materials. So right now, next, I think, couple of months, we'll have this wrapped up. I'm working with a couple of students to actually do similar analyses with of order 1,000 materials at once. So we'll be able to actually see, are there really interesting materials that can get us appreciably new sensitivity that are not radioactive. So I'll come back to you on that point in a couple months. Yeah.
So by the way, so the previous slide, yeah. The some of the material is sensitive to the even KV range dark matter. Right? So then I expect the energy deposit is around the million electron volt. But
Yeah.
What device did you assume here?
Oh,
Because
yeah,
the
no,
PS is not sensitive to
This is very important. These are not realistic reach curves in
Oh.
terms of threshold. Here, these are basically threshold free. We're going to get to the evolving threshold very soon. But basically, as a quick answer, right now, the best we can do is right around here.
Right.
Okay. Other questions at this point? Okay. All right. So now that we've built up some language to talk about the condensed matter systems, and how they interact with dark matter scattering. I want to come back to this issue of directional sensitivity that I mentioned at the beginning of the talk. And in particular, I want to take advantage of what we just learned about these heavy fermion materials to design directionally sensitive experiments. Let me explain what I mean. Here, what made that heavy fermion material so useful for dark matter scattering is that the plasmon was kinematically accessible, right? What if you had a material where you basically had an electron that was only heavy in one direction? Then the plasmon would be heavy, would be accessible rather, in one direction and inaccessible in the other directions. So you would have a large anisotropy in the scattering rate. And this turns out to be not that rare, actually. It's actually totally reasonable in the condensed matter context to think about electrons having anisotropic effective masses. This is actually something that's very common. In a typical material, the electron band structure has these anisotropic features. So what we're going to do now is just say that the energy of an excitation of a material is going to have independent contributions from different masses in different directions. This is a toy model of an anisotropic effective electron mass. And now you want to see, given that assumption, what happens to the loss function? What happens to the dark matter scattering rate? Well, I do want to just preface this exercise by showing you that indeed there are materials that exhibit large differences in the effective mass in different directions. So, for example, black phosphorus has a heavy direction, which is 9 times heavier than the light direction. Bismuth has a heavy direction that's 230 times heavier than its light direction. So you can easily imagine finding a system that has a substantial anisotropy in the effective electron mass. Let's just walk through how one actually does the computation. If we go back to the isotropic case, to the ordinary random phase approximation calculation, remember it's this one bubble diagram that gets resummed. So the RPA response function is given by the geometric sum of this bare response function, what I'm going to call chi naught over here. And that is what gives you this plasmon resonance over here in the denominator. Now, this isotropic bare response function is just the one loop integral. What we're going to do now is redo that one loop integral, just putting in this new dispersion relation that takes advantage of the fact that we have these different masses in different directions. It turns out there's a really nice coordinate transformation you can do. It's an easy trick. I can explain it another time. And it turns out that all you have to do is, instead of taking the bare isotropic response function as a function of Q and omega, just transform Q. Just rescale Q by the square root of the ratio of the geometric mean of masses to the mass in each direction. And that gives you a new chi naught that you can now put back into the expression at the top, and you get the full anisotropic RPA response function. Once you do that, what you now expect to see is that you have a heavy direction where the plasmon sits low, that's the dashed curve, and light directions where the plasmon sits high. So you expect, again, the scattering rate is going to be higher in that heavy direction. It's like having that heavy fermion enhancement just in one direction. Well, let's see. So this is an actual computed loss function in this toy model, where the usual axes are here. That's the accessible region for dark matter scattering. And now we have a low electron mass direction and a high electron mass direction. You can see that plasmon is sitting inside the accessible region only in the heavy direction. And that actually gives you a strong daily modulation as Earth turns on its axis. So for different ratios of the dark matter mass, in this case, to the mean electron mass, you can see that you get easily between order 10% and order 1 modulation. Now, what I'm gonna what I want to sort of abstract from this is just that this modulation, this anisotropic sensitivity, as with most of these modulation style experiments, it actually is like a threshold effect, right? It's basically you have some excitation that only can be excited in one direction. So what this ends up meaning is that where you get the largest modulation is in parameter space where you are sort of just able to excite one direction, not the other. And that actually is what these plots are showing you. So for example, so here, this is the dark matter mass on this axis. This is the inverse Fermi velocity over here. And basically right along this line is where the dark matter can just excite the plasmon in the heavy direction and not, I'm sorry, just where the dark matter can only excite the plasmon in the heavy direction when it's pointed in the heavy direction. So that's a threshold effect that is effectively tunable. This is the really important idea. That now, if you want to build an anisotropically sensitive experiment, you can now go and choose materials that have anisotropic sensitivity in the mass range where you expect your dark matter to live. Now, with the next 10 to 15 minutes, I want to take all these ideas we've just discussed and move them into the real world. I want to talk about real detectors. Any questions before we talk about actual detectors? Please.
So like the directions of the heavy direction, they are always fixed. There is like no way that they can also change.
That's right. I mean, that's actually very important that you have to have a material which you make a crystal that's ordered enough that you have a consistent heavy direction. In fact, in some materials, you would naively have a heavy direction, but you don't really have one in a bulk sample because they don't, it's not an ordered enough crystal. Okay, let's talk about real detectors. And I am very happy to be able to talk about this paper because it literally was just submitted. So here, let's talk about superconductors as detector systems. And here we're going to be able to use all the same technology that I've been talking about with dielectric functions, loss functions, all the rest. But now we're going to do it in systems that have very low thresholds to Duggin's point. So what is the whole idea of direct detection? Again, we want to induce some measurable transition in a system. If you're used to thinking about atoms, for example, you might be thinking about ionization as a transition of interest. For a superconductor, though, the transition of interest is the Cooper pair breaking process. You have this gap in the superconductor that corresponds to the energy it takes to unbind the Cooper pair. And if you can do that, in principle, you can make a measurable signature. What is nice about this Cooper pair breaking process is that the threshold for doing it is very low. So whereas ionization, for example, has typical energy scales of an EV, Cooper pair breaking has a typical energy scale of order milli-EV or even lower. So if you can detect the breaking of Cooper pairs in your superconductor, then you can achieve, in principle, a very low threshold. Now, for the purposes of what I'm about to show you, you really can just think about the superconductor as a dielectric system. If you were to think about it as a bunch of free electrons, where you just sort of kick an electron above the Fermi surface, this is the way people first thought about superconductors like 10 years ago, you would get a very wrong answer. But if you use the RPA dielectric function that I've been telling you about, then you will get an answer that is reliable if you are still well above the superconducting gap. If you're working very, very close to the superconducting gap, there are additional corrections that one needs to take into account. We're not going to be quite in that regime here, so we don't have to worry about that. Now, what is actually happening when Cooper pairs are broken? It's a bit of a heuristic description, breaking Cooper pair. What really happens is a little different. Really, a Cooper pair is some bound state of electrons that are talking to each other via phonons. But we should think about this as the superconductor having transitioned to a different ground state. Right? So below some critical temperature, now we have a condensate of Cooper pairs. The Hamiltonian looks like this. If you diagonalize this Hamiltonian, you find the elementary excitations, you will find that there is a new set of elementary excitations. It's not the simple electronic excitations. It is these Lagoliabov quasi-particles, which heuristically are kind of like linear combinations of electrons and holes. And really what one is doing when you break a Cooper pair is not so much just unbinding two electrons and making two free electrons in the superconductor. Really what you are doing is you are pair producing quasi-particles. So if we can make our dark matter pair produce quasi-particles and then be able to detect the presence of those quasi-particles, we can do dark matter detection with superconductors. Now, in order to understand what to look for, we have to understand not just the quasi-particles as they're initially produced, but also what happens to them after they are produced. In fact, there's a whole sequence of steps that happen. So after you make an energetic pair of quasi-particles, each quasi-particle can then basically brem off phonons in the material. Those phonons can then pair produce quasi-particles, and so on and so forth. So really what happens if you have a hard scatter and you make an energetic pair of quasi-particles is that you will end up in the final state with a big shower of quasi-particles and phonons. And for a typical material, about half of the energy will be in each of those components. Now, in a future experiment, what we would really love to be able to do, and we might be able to do in not that long, actually, is to detect individual excitations, to actually track individual quasi-particles and phonons. And if you can do that, then you can get basically all the way down to the superconducting gap. The gap, remember, is the energy that it takes to break one Cooper pair, right, or to produce one quasi-particle pair. So if you can really read out the presence of one quasi-particle, then you can get all the way down to below the milli-eV scale. For right now, though, we're not there yet. Instead, we have detectors that operate based on macroscopic properties that change in the presence of Cooper pair breaking processes. So I'm going to tell you about two examples. One is a platform called the Superconducting Nanowire Single Photon Detector, or SNSPD. So we had a prototype SNSPD detector that actually was able to deliver new constraints on dark matter with a very short runtime and a very small sample, just because it was able to achieve a lower threshold than any other experiment had ever achieved. And I'll show you a little bit about how this works. So in SNSPD, these nanowire detectors, they operate on the principle that the dark matter scatter causes a phase transition, causes you to leave the superconducting phase. And you might be used to thinking about superconductivity as a phase diagram that looks like this, where you have resistivity above the critical temperature that drops to 0 below the critical temperature. This is actually just one slice through the full phase diagram. And actually what matters for these nanowires looks more like this, where as a function of not just temperature, but also magnetic field and current, you can have this phase transition. So what happens in a nanowire is that you hold the current very, very, very close to the transition. Dark matter scatters. It creates a little tiny hotspot. That hotspot transitions out of the superconducting phase. Now, what does the current do in this nanowire? It flows around the hotspot. That increases the current density on the sides of the hotspot. But the current there was already really close to the transition. So now the current to the left and right of the hotspot suddenly transitions out of the superconducting phase. And the whole wire becomes a normal metal. And suddenly you have resistivity across the whole wire. Now, that is the basic idea. But one thing that we learned well after the prototype was even constructed, actually, is that there's another effect that one should really bookkeep here, and it will become more important in future experiments. And that's actually the geometry of these detectors. So a nanowire, as the name implies, is not a bulk volume. It is a wire. It really looks like layers. And if you have thin layers, that actually changes the boundary conditions and changes the dielectric response of the system. So if you work in the macroscopic language of classical E&M, it's actually pretty easy to figure out how these boundary conditions change the dielectric response. You can compute basically an effective loss function that accounts for the effects of the boundary conditions in the system. And you'll find there's actually an enhancement to the scattering rate just because of the fact that it's a thin layer. This, again, is something we did not know when we built this device. Now, let me show you what this enhancement actually looks like. Here, each of these curves shows the loss function for a different thickness of material, essentially, different layer thickness. So on the horizontal axis is the energy, and I fixed this so that 1 is the usual plasma frequency. That's where the plasmon should sit. And this curve in orange, that's the bulk limit. That's where the system is thick enough that in particular, the length is much larger than 1/q, inverse momentum transfer. There, it looks like an ordinary plasma. As you shrink down the system and you go to the thin layer limit, these surface effects actually dominate, and you end up with a plasma that shifts to lower energies and gets higher. That is exactly what you want if you want to look for light dark matter scattering. You want a large loss function at low energies. So that seems useful. Now, given that, where do we actually expect these effects to become important? Well, it's again about this competition between momentum transfer and the thickness of the system. Right? So, in our case, with these nanowires, the layer thickness is 7 nanometers. That's the only layer that actually matters here. And that turns out to translate to momentum transfers of order 30 eV. So that should mean that you get the biggest effect for dark matter masses below about 100 keV. And now I want to make the point that this is only something that we, again, we recognize this ad hoc after the system was already built. If you want to go and build a system that is optimizing for these layer effects, in principle, that can give you targeted sensitivity to different dark matter masses. And that's something that a student and I are actually working on right now, and hopefully will be out later this year. So let me show you what you can do with these nanowire detectors. This blue region here is the constraint from the prototype detector. So this is a tiny device that was running for about a week, and it was actually able to carve out new parameter space just because the threshold was so low. So the threshold for this device was about 0.7 EV. The other curves on here are projections based on the progress of this nanowire platform. So in particular, this green curve here, there actually exists a prototype device that has this lower threshold. Now, the dashed curves here are showing you the effects that you get from thin layers. So you can see it's actually not important for the blue curve for the current constraints, but the next generation constraints actually may get 3 orders of magnitude enhancement just from being a thin layer. And that's not actually optimized for being a thin layer. That's just assuming the same geometry. Here's what you would get. Now, we actually have experimental collaborators who are preparing an underground run of these devices, because right now the background is consistent with cosmic rays. So it actually makes sense to do an underground run. But here's the problem. How would you actually scale this up? Here, this is a tiny prototype, right? If you want to get from this to this, you need to do more than just making the device have a lower and lower threshold. You need to make it larger. And if you want to make it larger, that effectively means having many of these devices that you read out at the same time. That's hard to do with these devices. Fortunately, there is another device where that's not hard. And those are kinetic inductance detectors. So now we finally get to today's paper. So kinetic inductance detectors, which you can read about on Sunday night, these are detectors that operate on a similar kind of macroscopic properties principle as the nanowires, where you're not looking for individual excitations, you're looking for a change in the properties of the superconductor, but you're not looking for a phase transition. Instead, the idea is that the kinetic inductance actually increases with the quasi-particle density. So if you scatter in the material and you produce some free quasi-particles, you basically make an inductor. That is actually very helpful, because if you put an inductor into an LC circuit, now it has a very well-defined resonance frequency. And you can actually watch for that LC resonator to move around as the inductance changes, and you can register that energy was deposited. So again, a prototype device. This is actually an electron microscope picture here, even though it looks like a drawing. And we have a 15, this whole thing actually, about 22 nanometers thick as a layer. That is our inductor that's going to receive scatters from the dark matter and translate that into a shifting resonance frequency. What is so nice about these is that these LC resonators are really, really easy to stack up. It is really well established in the experimental world how you can wire these together and easily have arrays that are thousands or even tens of thousands in size. That's already been done. So if we can use these to detect dark matter, it becomes practical to actually scale them up. And in fact, we now have a prototype device which is able to set constraints on dark matter in the same way that our nanowire prototype was able to do so. This one, I'm going to skip the calibration details, but just bring you to this take-home message here that it achieves a threshold of about 0.2 eV. So it does better than the nanowire even by a factor of a few. And this device actually is about 10 times lower energy resolution than the best-in-class devices today. So there's actually considerable hope even with similar platforms right now. And there's, it's sort of obvious to the experimentalists at least that you can actually achieve another factor of 10 or so by going to different materials. So there's actually real hope with these devices to get down to really substantially lower thresholds. So here is the situation now. We have our new prototype device, which, as you can see, is a little bit better than the nanowire over here, because it can go again to lower thresholds. Now we can make projections for future devices. This orange curve here, that's what you would get with an array of 10,000 devices, which again has been achieved in the past already. That's realistic. And this is just using the same kinds of materials that we used for our prototypes. So nothing exotic here, just more engineering. And then if you do go a little bit more exotic and you use a material that has a smaller superconducting gap, which exists and are very well handled by experimentalists that just haven't been used for this purpose yet, then you can get to that green curve and you can really start to probe large parameter space down to the KeV scale. So I'm going to basically wrap it up here just by pointing to these realistic projections for future arrays. I'm just going to leave you with a couple of thoughts about the future of light dark matter detection. In particular, that we have now come a long way in being able to use condensed matter physics for dark matter physics. We are in particular able to do this to engineer anisotropic systems, where we can actually get a directional sensitivity to dark matter scattering. And superconductors are actually implementing all of these ideas. Everything that I talked about for the first 40 minutes of the talk is now being realized in the lab, and there are really good prospects for the next 5 to 10 years. So hopefully we're going to be able to test a lot of new physics over the next 5 to 10 years, but for the next 5 to 10 hours, I will be upstairs in the visitor office, and you should by all means feel free to come say hi or send me an email later. All right, thanks everybody.
Okay, so questions for today?
So, I think that I didn't catch the background details. So what are like the backgrounds that I should be aware of? Because like we are kind of working near threshold and it's like a very small energy transfer. And if we are like in the condensed matter system, there can be like some extra fields lying around. There can also be some thermal effects. So is there anything that should be worried about?
Yeah, so there's a couple of things. So as you mentioned thermal effects. This is actually very important. So because of those thermal effects, what we have to do for any such experiments is cool the system so the temperature is much less than the excitation of interest. That is, one of the limiting factors actually. So right now, the projections I was just showing you for these kinetic inductance detectors, they could be much more effective if it were really easy to cool things down to 10 millikelvin. It's not. So that green curve I showed you assumed 100 millikelvin. Now, other sources of backgrounds, we're definitely going to have cosmic rays. We've already seen that in both the nanowire and kinetic inductance detectors. In the kinetic inductance detectors, we'll probably have electronic sources. This is something where we already have seen that to some extent in the kinetic inductance detectors. This is something that the experimentalists are still working to give us a full story on. But this is why, again, directional sensitivity is so key. Because if you actually are sensitive to the direction of the incoming scattering particle, then you can ignore your background.
So, but like if I'm just stacking together different devices, and if the backgrounds start also adding up, won't it can't it lead to some problems? So even though like the background is small for one device, and now I'm stacking like thousands or millions.
Yes, so you will have large background counts probably. I mean, look, this is the story of large xenon detectors, right? They had to go through so many iterations to reduce their backgrounds as they went to lower and lower sensitivities. Ultimately, there are two things that give me hope on this front. One is that so far, we've actually been very, very lucky in removing these noise sources and identifying them. The other thing is just that, again, this directionality is actually extremely powerful, even if you have a large isotropic background. It does limit you, but the scaling becomes more favorable. So basically, as a rule of thumb, if you're background limited, then the rate at which you can progress through the parameter space scales as the square root of the exposure. So ordinarily, if I have no background, right, then how far I can get down in the plane goes like the mass times time of my experiment. If I have large backgrounds, it goes like square root. If you have this anisotropic component that you look for, it goes back to being linear. So you may take a linear hit, but you'll still scale linearly with the exposure.
So what's the scale of the other existing prototype?
The prototype kinetic inductance detector. It is very small. It is of order picogram in mass, 10 picograms, I think.
Do we have to consider the cosmic wave background and then the issue?
Yes, and the reason is just that the cosmic rays are so energetic that if they hit the substrate, it'll leak into the absorber. So the thing is that when we're doing the dark matter constraints, we want to be very conservative and say we're only going to see the dark matter if it hits the actual tiny device. But realistically, that device is coupled to a lot of other stuff that's connected to the substrate. So the experimentalists who set this up know that if they hit the device with a large energy deposit that's far away from the actual small absorber, it will actually respond to that deposit.
So wait, so then, so your detector is effectively, the fiducial, well, not fiducial volume, but effectively the volume is larger than.
Yes. So, look, I would look, so this device, right, is like, you have a tiny absorber here, and you have a massive capacitor that it's connected to, and that's all put onto a huge substrate that's many orders of magnitude larger. I would love to be able to use this whole volume and say I'm setting dark matter constraints using this fiducial volume. It is only me being conservative that stops me from doing that and saying, okay, well, really, we should only use the calibration that we've done that was in this absorber. But what you could do, and what I have been fighting with experimentalists to make happen for some time, is to basically calibrate on the substrate, right? To say if I hit the substrate with a photon, can I register that in the absorber? The answer is probably yes to some extent. The fiducial volume is probably, the effective volume is probably much larger than what we've used for these constraints.
Okay. Any further questions? So if not, the rest of it together.